column, such as the plume top height or the height at which ash is dispersing. And depending on their complexity, they also incorporate parameters such as atmospheric parameters, wind stratification, and so on. And then you can, these models are widely applied, for example, to reconstruct the dynamics of past eruption from the deposit. During volcanic crises, they are used in near real time to invert plume height and have an idea of what the mass eruption rate is, and then that's used in the dispersion model. And they're also widely applied to plan for future eruption. And so recently, there was a really important and kind of innovative for this community exercise called the eruptive column model intercomparison exercise. So that was in 2016, where all the different modeling groups came together and compare their model predictions for two different eruption case studies. And so when you have such a model intercomparison exercise, generally one question you would like answered is how good are these models in the end? Like, are some model better? Is any model prediction satisfying, which is really not granted, especially when we talk about volcanoes and so on. But in terms of validation, I would argue that we are still a bit behind for volcanic plume model. So what I've put in this table is modeling communities and some reference paper of corresponding model intercomparison projects. And then the number here, you can just see the mention of the word evaluation or validation in the design paper of the intercomparison project. You can see that in general, the words evaluation or validation are really highly cited, except in this eruptive column model. In particular, in communities such as climate science, the evaluation component is really key. Of course, these communities have been doing intercomparison for decades, so we are lagging behind, but they have devoted software, devoted data set. It's all very well organized. The eruptive column model intercomparison project was still, of course, very valuable. And also I want to highlight again, it was a first. But for this first version, there was no aim to evaluate the models, neither against observations or experiments. And I think that's really something that we should aim for the future. And actually, that's not me saying it, but it was directly mentioned in this intercomparison study. And so that's really what motivates now the IVESPA project is to answer that need. And so what sort of data do you need to evaluate a volcanic plume model? This is a figure from a paper by Larry Mestin in 2014. It's just showing how the plume height above the vent depends on the mass eruption rate on a log scale here. And so in this figure, all the different symbols correspond to different eruption. And then each box here, each rectangular box is the minimum and maximum prediction of a plume height model that Larry was testing. And on top of that, you can see the black line, which is kind of the best empirical cover of it. And so what this graph is, what I want to illustrate here really is that the two key parameters you need to evaluate plume models are the plume height and the mass eruption rate. And most critically, this needs to be estimated independently, because if you want to evaluate a model, you need both the input and the output, and you need this to be constrained independently. Otherwise, you don't have a suitable data set for model evaluation. So that's really the two key parameters you want, but then you could also add atmospheric conditions depending on the complexity of your model. Some models require grain size distribution. This data set is from 2014, so you may ask if there's an updated version somewhere, if you have an evaluation to do, where are the uncertainties on this, and so on. So there's lots of other consideration beyond having the mass eruption rate and plume height independently constrained. And so here I'm just summarizing some of the main features of predecessor data sets that have independent eruption source parameter. So in particular here, you can see the number of events in data sets, which has tend to increase with time, but not always. We comment on why. So all of these data sets aim to have strictly independent eruption source parameter, but one constant problem in the literature is that mass eruption rates are very often estimated from the plume height, and sometimes it's not clear when that was the case. And also plume height are sometimes estimated from the deposit, in which case you could argue they are not completely independent from the deposit properties and thus your erupted mass estimate. So not all of these data sets have strictly independent eruption source parameter. So recent data sets tend to include atmospheric data, but that's not the case of all. Or sometimes they may use simplified atmospheric data, like this data set by Giro and co-author. Only a few data sets include total grain size distribution, and that's just because it's less commonly constrained. In particular, you can see that the data set that do include them, they have a lot less events, for example, 5 or 9 and 10 for this one. Surprisingly, because we are talking about volcanoes, we always have huge uncertainties. We can see that most data sets do not include uncertainties, or at least not systematically. And then only a few data sets are community-wide default and online open access database. So really what we've been trying to do with IVESPA, which is now this last column, is to kind of address all these limitations and have a new product that does include all these features and is also extensive in terms of the number of events considered. So what is IVESPA? First, don't forget the I. If you Google IVESPA, that's most likely what you're going to see. So we are not doing a scooter for volcanologists. So it stands for Independent Eruption Source Parameter, Volcanic Eruption Source Parameter Archive. Even I got my acronym wrong, so that's a bit deceiving. But essentially, it's going to be a new database of independently estimated eruption source parameter. It's endorsed by IFSA Jeffra Hazard Modeling Commission, and we are also supported by the British Geological Survey. And then the primary science objective, again, is to support the evaluation and development of eruptive cloud models. And I would just skip that because that would be repetition. So now we just start by giving you a brief overview of IVESPA and what's actually in it. So just starting with a map of the volcanoes that contributed events to the database. And on this map, the larger the triangle, the more event the volcano contributed. So you can see we have 2 large contributors. We have Mount Druidopt here and Etna here. But overall, we have volcanoes that really covers all latitudes, which is interesting for atmospheric conditions in particular. And then you don't see it here, but I just want to highlight that these 2 volcanoes, Etna and Druidopt, just themselves as many events as some predecessor database had in total. So that means you could start doing volcano-specific or maybe region-specific. For example, we have over 12 events in Chile, calibration of your plume model, which is quite interesting. And then that's just the temporal distribution of the events included in the database. So obviously you can see that we have more events on the recent decade, except for the last decade. That's just because there's a lag between the time people go on the field, study a deposit, and publish parameters. So that's why we don't have as many events for the last decade. So I just want to stress again that all the events in IVESPA, they have independent estimate of the total mass of tetraph fallout and the duration, which gives the mass eruption rate, and then at least 1 plume height and also atmospheric conditions. So all of these parameters, they are systematically included. But then we also include a range of other parameters that could be useful for volcanic plume modelers. And this figure here summarizes their availability. So first, if we look at the height, in contrast to other data sets, we don't provide a single height, but we clearly distinguish 3 types of height, either the top height of the ash plume, the spreading height of the ash plume, or the SO2 height. And so you can see that the top height is available for most of the events. I think it's all but 3. Whereas we have the spreading height and the SO2 height for roughly a quarter of the events in the database. But there is always at least one of these 3 heights available again. Then other eruption source parameters we've collected include, for example, the mass derived from pyroclastic density currents, the exit content of water vapor, exit temperature. And you can see these are generally available for between 30 and 70% of the eruption age. TGSD is the total grain size distribution, and this was rarely available, but still we have it for 20% of the event. So that's roughly 25 events where we have all of the mass absorption rate, the plume height, the atmospheric condition, and the total grain size distribution. Then we collected categorical parameters such as the eruption style or the plume morphology. So by eruption style here, I'm going to mean either phreatic, phreatogmatic, or magmatic. And then plume morphology is weak plume or strong plume. So weak meaning strongly bent over plume. And then we collected additional data such as data informing the quality of the deposit sampling, in how many locations was the thickness of the deposits measured, and that in turn informed the quality of the mass of tephra fallout and mass absorption rate estimate. So in IVESPA, I don't think I've made that clear yet, but all the data is collected from the literature by the working group. And so one common problem when you try to gather data from a study from the literature is that you often have to interpret what a paper say, either because an interpretation, information is missing, or maybe something is not clear. So for example, something we run into very commonly was plume height quoted in kilometer, but you don't know if they are above sea level or above vent level, in which case you may just have to go ahead and make an assumption based on what you understand of the paper. And so to inform how much we had to interpret the literature in providing you eruption source parameter, we came up with what we called an interpretation flag system for each eruption source parameter provided in IVESPA. So this diagram here tries to give you a rough idea of how we came up with this flag. So the x-axis here is our confidence that the interpretation we made when necessary was correct, going to higher value toward the right. And then the y-axis is how much the interpretation we made impacted the parameter value in the end. For example, say you don't know if the plume height is above vent level or above sea level. If your vent height is 100 meters, it doesn't really matter. If your volcano is 5,000 meters, then that's a big difference in the end on the plume height. And so overall, flag 0 is when we had little interpretation to do, or when the interpretation had little impact on the parameter value. Whereas flag 2 is when we have a lot of interpretation to do, sometimes even educated guess, or when even a small interpretation had a big impact on the parameter value. Yeah, I can come back on interpretation flag later if needed. Okay, so in addition to try to inform how much interpretation we had to do from the literature, we tried to implement a robust data quality control procedure. So to do that, for every single event in the database and every single key eruption source parameter, we had at least 2 members of the working group reading independently the literature and then coming up with their own estimate of parameter value, and then discussing to reach a final consensual value. So this graph is showing you the corresponding example for the total erupted mass of tephra fallout. The y-axis here is the initial estimate by one of the member of the working group, whereas the x-axis is the final consensual value reached after comparing estimate from several members. And that's what essentially is in the database. And then the dashed line in the middle is the 119. So you can see that as expected, most of the time, there was an excellent agreement on estimate for the total erupted mass. But you can also see some strong outliers. For example, these dots here, they have 2 or 3 order of magnitude difference. So these outliers, generally, they are just correspond to misreporting by one of the co-authors, or maybe a volume that wasn't converted to mass, and this kind of error. And so even though these are trivial mistakes, the fact that they are here means that if you don't have a quality control procedure in place, that's the sort of error you may end up with in the database. So hopefully we got rid of most of them, but I think it's really important to have 2% checking. And then even if you forget about these major outliers, you can see that some data points are still like discrepancies by a factor of 2 or 3 left. And that's just the reality of how complex the literature is when it comes to gathering eruption source parameter. And I just want to highlight all these dots are color coded by interpretation flag value. And so the light blue stars, like this data point here or this one, are data for which we had significant interpretation of the literature to do. And you can see that quite reassuringly, all these points, they fall fairly close to the 119. So it means that even when we had a lot of interpretation to do, the different members of the working group generally agreed on what the value should be. So briefly, I just want to show you how the distribution of key eruption source parameter in IVESPA. So TEM here is the total erupted mass of tephra fallout, and from that and the duration, you can then get the mass eruption rate. And then these are the 3 different heights we had. And so what's really important, if I compare to the range in the predecessor data set we amassed in 2014, you can see that in IVESPA, we cover a more extensive range, in particular for a smaller magnitude eruption, but also for duration and even for height. These are the relative uncertainties distribution for all of these parameters. So not surprisingly, there are order of magnitude uncertainties sometimes on the total erupted mass of tephra fallout. You can see that the plume height and the duration also have uncertainties that can be quite high. And then these are the value of the interpretation flag that we attributed. So again, 0 is no interpretation, 1 moderate, and 2 significant interpretation. And we gave this flag for both the best estimate provided in the database and also the uncertainty on the best estimate. And so something that really stands out is that the duration, you can see, is one of the parameters where we have the most flag 2 for the best estimate. And you can also see in the uncertainty distribution that there isn't really a tail. So that parameter was really hard to constrain most of the time because the information to place an end and a start on an eruption were quite hard to obtain. And last, I've said that, but I want to highlight again that we do have atmospheric conditions for all of the events in IVESPA. And in addition to having atmospheric conditions, we provided them from 2 different climate analyses, so 2 different data sets. And I want to illustrate here why this could matter. So this figure is showing horizontal wind speed profile for 2 events in the database. So in red is Agung, 1963, one of the phase. And then in blue is Chaiten 2008, again, one of the, I think it's 3 phases we have for Chaiten. And then the circle continuous line is the atmospheric profile from the ERA 5 analysis, and the dashed line with triangle is from the NSEP and CAR analysis. And you can see that for Chaiten, which is a recent eruption, so the climate analyses are well constrained, there's a very good agreement between the 2 analyses. But for Agung, it's not the case at all. And there is difference, for example, here by a factor of 4. In the local wind speed at that height. And then if you look at the average wind speed over calculated over the column height, this histogram here is showing you the relative difference between the NSEP and CAR value and the ERA 5 value. So you can see that most events have relative difference below 10%, meaning a fairly low uncertainty on wind speed. That's how you can interpret it. But still, we have over 15% of the event in the database where that difference exceeds 30%. So first, we have atmospheric conditions, but we have 2 data sets, and that enables constraint uncertainty. And that uncertainty is actually quite big. So I think it shouldn't be overlooked. So that's it for giving you an overview of IVESPA. Now I'm briefly going to go over some of the work we are starting with the working group to apply the new database to constrain some of the plume height scalings relationship. So very simple model linking the plume height to the mass eruption rate. And so I'm going to start with what I would say is a canonical relationship between the 2. So this power law relationship between mass eruption rate and plume height, which is applied by many volcanologists and also in very commonly in dispersion model. So here I chose to show you the mass eruption rate as a function of the height, precisely because that's the way it's commonly applied in dispersion model, meaning they have the height available and they want to retrieve the mass eruption rate. So all the triangles are events from IVESPA. I didn't include uncertainty just because that graph is going to become a bit more busy. So, but we do have uncertainty on this. And then the blue line is the new power law relationship we constrained. And the pink dashed line here for reference is the one from Mastin et al. 2009, which I think is the most used nowadays. As you can see, they agree fairly well, but if you look at high mass eruption rate or high plume height, then the difference between the two relationships start being pretty important. So there's a half order of magnitude difference in the predicted mass eruption rate here. And then what's really interesting with IVESPA, I think, is that in addition to having the top height of the plume, we also have the spreading height, at least for some of the event, which is shown here as purple square. And the corresponding power law relationship is shown in purple as well. You can see that not surprisingly, if you look at a given mass eruption rate, the spreading heights tend to be lower than the top height. And that's not simply surprising, but just by constraining that, it means that Volcanic Ash Advisory Center, for example, can use the specific height they have available, a model specific to the height they have. So if they have the top height, they can use the blue relationship, and the purple line, they can use the purple. And last, sorry, I pressed forward a bit too fast. We also have data for the SO2 height, which is here in yellow. And again, the corresponding power law relationship. You can see SO2 height generally falls in between the top height and the spreading height. Obviously, there's lots of variability around this main power law train. So the big question is, can more sophisticated models do a better job? And in particular, in that case, I'm going to look at a scaling model still. So relatively simple 0D model. So I'm just going to talk about 4 select scaling examples. So the first line in this table is the one I just talked about, the power law relationship between the mass eruption rate and the plume height. And so that's an empirical scaling. Another really classic scaling is the Morton, Taylor, and Turner scaling, which links the mass eruption rate to the power 4 of the height and the stratification raised to a power 3. And this one is analytical. And then there is a range of other scaling that was proposed recently, but I'm going to show you results for the one of De Gruyter and Bonadonna 2012, which resemble the Morton and Taylor and Turner scaling, but with a term pi here that incorporates wind effect. And then last, I'm going to show you a completely empirical scaling, which is just an extended power law relationship with the stratification and the wind incorporated. And so what each of these graphs shows you, the y-axis is always the scaling predicted mass eruption rate based on the plume height. And the x-axis is the mass eruption rate in IVESPA, so derived from the field reconstructed mass of tephra and duration. And then the red line is always the 1, 1 line. And so again, the top 2 scalings are analytical scalings, whereas the bottom 2 are empirical scalings. And then the 2 right scaling do account for wind, whereas the other one doesn't. The top left one accounts for stratification. And then if you look at the value of the coefficient of determination here, so how much variability is explained in the data, you can see that the Morton et al. Scaling has the lowest R-square value, and the empirical power law fit with wind and stratification as the highest value. And if you take time to look at the graph, you will see that indeed there is more scatter in this top left graph than bottom right. And then if you look at the difference in R-square value, for example, between these 2 scalings, you can see that atmospheric condition may explain up to 5% of the variability in the mass eruption rate, which is a very small fraction, but don't forget that the mass eruption rate varies over 7 order of magnitude, whereas wind and stratification varies by a factor of 2 to 10 at most, 10 for the wind and 2 for stratification. And then something a bit disappointing, but maybe not so surprising, is that the analytical scaling at the top can't perform as well as the empirical scaling. And in particular, even an empirical scaling that does not account for wind and does not account for stratification still performs better than an analytical scaling, that accounts for wind and stratification. And so on the next slide, I'm going to pick this empirical model here and just show you a bit more how the residual of this model depends on other eruption source parameter that we provide in IVESPA. And so again, this is the mass eruption rate residual for this model on the log scale. And here on the x-axis, I'm showing you the magma water content that we collected from a petrological study. So even though there is a lot of noise, you can see that there is a positive trend in this data, and the trend is actually significant. And that's really expected because the magma water content or the gas content of the plume is going to affect the plume buoyancy flux, which is indeed what governs the plume height, and not just the mass eruption rate, but the buoyancy flux is what matters in terms of plume dynamics. Another parameter that we've tested is how this residual depends on the median grain size distribution. And essentially here there is no trend. We also have a lot less event for which the grain size distribution is available. One where we're really expecting a trend. So here I'm showing histogram of this residual, and the red histogram is for phreatomagmatic eruption, and the blue one is for magmatic event. And here you can't really see a difference, or maybe a small one, but like, there is really nothing clear. Whereas we were kind of hoping to see the eruption style influencing the model prediction. And then last, it's same sort of histogram, but here I'm showing you all the event from month end now versus all the event from month reduct. And here you can see an important difference between the two histograms. And that could just be linked to bias in the way the data was collected or processed at the two volcanoes. So there may be systematic differences, but there could also be more physical effect at play. For example, in the Etna, the tephra plume is coupled to a lava fountain. And that could explain why the model error is systematically different from that for Montreal, for example. So that was just some result for 0D model. So we are it's currently ongoing work. So everything I showed is a preliminary result, but we are testing more 0D model and pushing this analysis a bit more. In the future, we really hope that IVESPA will be applied to evaluate 1D and 3D model, and in particular should be used as a component for a future eruptive column model interpresent study. And then we also hope, like there's a range of other applications possible. For example, you could use it to design future eruption source scenario at volcanoes where there isn't a lot of information. Also, an application I'm really interested in is to see how isoplasterite height relate to SO2 height, which we now have, and that could help better reconstruct the climatic effect of past eruption, because isoplast height are more representative of the maximum injection height. So you could use IVESPA to see how the two relate. And then a very personal motivation, which I'm briefly going to talk about if I have time, is that I'm hoping to use IVESPA to better constrain the influence of atmospheric condition plume dynamics, and then in turn the potential impact of climate change on plume height. So very briefly, if you, because I guess that's probably not everyone has thought about or heard about, but some of you may have heard that climate change is expected to affect volcanic eruption frequency because glacier retreat, ice sheet retreat result in more frequent eruption. So that's an effect that's quite well constrained. Now, if you think about plume dynamics, as Earth is warming, the atmospheric conditions in which volcanic plume are rising are also changing. So that could affect the altitude reached by volcanic plume. So this graph here is showing you the altitude, the spreading altitude as predicted by a 1D plume model for an eruption at the Mount Pinatubo location as a function of the mass eruption rate. And then the blue line here is under present day climate or late 20th century climate. And then if you look at the orange and red line, it's exactly the same model run for the same source condition, but using atmospheric condition projected by climate model for the 21st century and the 21st century. And so you can see the plume height changing a lot. In particular, it's decreasing in the troposphere and increasing in the stratosphere. And that's a consequence of changes in the temperature profile in the tropics at the pinnacle location. And then I've added this horizontal dash line here, which show the height of the tropopause. And as Earth is warming, the troposphere is warming, so the tropopause height is expanding. And so you can see that you need much higher mass eruption rate in the future to reach the tropopause height. So I've just said that. And so I'm really interested to know if IVESPA can help to confirm or challenge this hypothesis on how plume height is going to evolve in the future. And this could have quite important consequences in terms of climatic impact. So I think given the time, I'm going to jump over most of my remaining slides, but I just want to illustrate. So if I take an eruption at a mass eruption rate of roughly 10 to the 6, 510 to the 6 kilogram per second. So an eruption that nowadays would reach pretty much hit the tropopause exactly. And what's happening to the future eruption? Why does it matter that the plume height doesn't change, but the tropopause height is rising? So if you run these two cases for a climate model, I'm gonna jump forward a lot. That's the corresponding evolution of the stratospheric aerosol optical depth following the eruption. So the stratospheric aerosol optical depth is how much volcanic aerosol blocks sunlight following the eruption, and that's directly related to how much energy is removed from the climate system by the eruption and how much cooling, volcanic cooling you get at the surface after the eruption. So the blue line here is for an eruption in the present day climate that does reach exactly the tropopause, and the aerosol, most of the aerosol end up in the stratosphere and have a long lifetime and exert a significant SAOD perturbation. And then the red line is the same eruption, but in a future climate. You can see that the SAOD perturbation is strongly dampened as a consequence of this change in plume height. And so I won't say much more on these effects, but just keep in mind that climate change has the potential to affect plume dynamics and in turn the volcanic impact on climate and how much cooling we get from volcanic eruptions. So jumping straight to my conclusions. So the IVESPA database is a new data set of independent volcanic eruption source parameter. And I hope you will find it features some important improvements over predecessor data set. And in particular, we hope that it will be widely applied to evaluate volcanic plume models. So we are currently doing the work for 0D model, but really it has everything needed for 1D and 3D plume model. And so the paper is currently under review. And I was hoping that we have a database website by this date, but I'm going to blame COVID, and we are a bit late with that, but we'll advertise it as soon as it becomes available. I want to highlight that you can already access the data or the manuscript. You just have to email myself or Sam directly. And if you want to get involved, or if you have ideas for what we should include, or if you have data that you think should be included in IVESPA, if you recently published a paper with a mass eruption rate of plume height, we are interested. So please be in touch with us. And thank you.
Thank you, Thomas. That was a really great talk. We have time for questions and discussion. Please go ahead and raise your hand. It looks like we've got Yoshi. You want to go first?
Hey, buddy. Nice talk. Glad to see this progressing, so I'm definitely going to take advantage of it. I had a question. So for Pinatubo and Calbuco, more recent eruptions, we have umbrella cloud spreading rate in addition to the spreading height data. Do you guys plan to include umbrella cloud spreading rate data to this data set moving forward?
Exactly. So that's a really good question. Thanks for asking. So that's a discussion we had when designing the database, and maybe I haven't insisted enough on that, but all the erupted mass and mass eruption rates we provide are derived from field deposits. It's so that there is more and more diverse way to evaluate this, and I think the biggest contender is mass eruption rate derived from umbrella growth rate. So we haven't included them at this stage, but that's definitely in our list of future development. We want to add a parameter for those eruptions that have mass eruption rate derived from umbrella growth. And similarly, I think when the radar estimate will have advanced a bit more, they should be included. And comparing these different mass eruption rates is going to be really interesting.
Thanks. Other questions out there? Yeah, Colin has a question.
Hey, Thomas, nice one. Just wondering about, it looked like on your scalings diagram, like all the small mass eruption rates are skewed, where the scalings are consistently greater than the field-derived mass eruption rates. Just wondering what's going on there and what kind of value you can add by adding all of the very likely huge range of observed small eruptions that may be complicated by things like transient dynamics and stuff.
Are you talking about that graph?
Yeah, that's the graph. And if basically all the small eruptions on at least 3 of the graphs kind of look like they're skewed with greater, scaling derived mass eruption rates. Yeah.
So, I mean, one hypothesis that some of you may have when looking at this graph is that this may be tropical eruption, and that here humidity may play a role. To reach the same height, you actually need a smaller mass eruption rate than predicted by the scaling because humidity is playing a role. But if that was the case, I guess we would expect to see that too for other eruption. I'm not showing latitude or humidity here, but that's definitely one hypothesis. And yeah, I don't really have more answer at the moment because I mean, this is very much preliminary result. Like we are exploring the data at the moment. But yeah, I think clarifying where some of this variability comes from is quite critical. And I guess that data point here is driving, is responsible also for some of the trends you see in the scaling and result in under-predicting the mass eruption rate for this guys. Does it make sense?
Yeah, I think so.
7 p.m. in the UK, so my brain may not be functional anymore.
It's okay, I'll pester you about it later.
Thomas, while we wait for other folks to chime in here, I had a question, and this is kind of forward thinking. You spend a lot of time, of course, gathering data that have been reported in literature. Do you have plans to use this, or do you have suggestions to use, better reporting so that it's a bit easier or more straightforward to incorporate into IVESPA?
Yes. In fact, I guess we have a lot of suggestions, and we try to make some sort of recommendation in the paper. But one thing that was really challenging in particular was uncertainty. Because uncertainty are rarely, I guess for plume height, they are quite commonly reported in papers. And for mass eruption rate, they are more and more assessed in a clear manner. But still, like giving a number for uncertainty, saying what was included in this number, what sort of uncertainty, saying what confidence level it is associated with. It's just like very rare to get this kind of information. And it made it really hard to come up with good uncertainty estimate. I think that's also why we ended up including this interpretation flag, because sometimes we had like very clear, rigorously assessed uncertainties, and sometimes it was not the case. And that's also why we split these flags between uncertainty and best estimate, because it could be very different. But yeah, we have a recommendation, and they will be spelled out in the paper.
That's great. I think other questions out there? I had one more, maybe, and that is, we're obviously focused on plume height. It's something that is a bit easier to measure. but you've also had some time, and you kind of alluded to this toward the end of your talk. You thought a little bit more about climate forcing associated with eruption columns, and plume height is part of this, right? But certainly the loading, the ash loading, aerosol loading versus height is also a big part of it. How much do you think we're capturing all this with just one number, the plume height, or do we need more information, do you think?
Yeah, I think in the climate community, it's definitely a constant debate that there's no indicator that says what the climatic impact was. Because, for example, the VEI doesn't incorporate the SO2 mass, or the same VEI could be tropospheric or stratospheric injection. So it's true we kind of lack that sort of indicator for climatic impact. And along that line, we also had a debate on whether to include SO2 mass in IVESPA. And in the end, we haven't, but that's definitely another development in the future. It's a bit tricky because some eruption, we split them by phase. Like, for example, Chai-10, I think we have constraint on the mass eruption rate for 3 different phases. I'm not sure how easy it would be to split SO2 mass for all these phases. For some eruption, it would be fairly easy, but for others, it would be more complicated. But that's part of the development we want to do, and that would also enable to link better with databases that are more climate oriented, like for example, Simon Carn and the NASA has a data set for SO2 injection and height that's very useful for climate modeling. So I should mention too that all IVESPA events are linked by eruption number and volcano number to the Smithsonian database. So that's one link that we've facilitated. But I think we can do better in terms of connecting with database from other communities.
Thanks. I see Yoshi. Yoshi, do you have another question, or is that just the old hand?
Yeah, I got another question,
okay.
As always. So there's some lower clouds spreading, for example, the Calbuco image you showed, and I'm obsessed with that stuff. In the database, are you going to include the heights of those lower spreading clouds, or is it only going to be the height of the main umbrella cloud spreading? And will you even note that there were observations of, say, co-ignimbrite spreading clouds for some of these eruptions and phases?
Yeah, so again, we have a huge list of development we want to do. So that complexity is not included yet in the database. What we will have done sometime is that if multiple heights are reported, and in some cases they may correspond to different intrusion, that's going to be reflected in the error reported for plume height. But exactly like you said, like in the future, we really need a flag for, say, where there are multiple intrusion, was it a multi-layer cloud, or for example, co-ignimbrite cloud. So yeah, not there yet, but it's a good suggestion, and we definitely will include it.
Well, I think this is probably a good moment to thank Thomas again. Well, again, if as long as Thomas has a few more minutes here, we might, if people have little questions at the end, we'll stay online for a few more minutes. But everyone else, join us again next week, and we'll continue. The schedules will keep going on the email list. If you're not on the email list and you'd like to be, you can either sign yourself up if you have a copy of that, or just email me and we can get you signed up. All right. Thanks again, Thomas. This was really great and good discussion.
Thank you. Thanks everyone for joining.